Hi students, today we will discuss principle of mathematical induction. Before going to discuss about principle of mathematical induction, let us understand one concept called mathematical proposition. Mathematical proposition is a statement, is a mathematical statement, a mathematical equality dependent on a parameter n, where n is a set, it belongs to the set of natural numbers. Okay, let's take a couple of examples. Suppose I say that 1 plus 2 plus 3 plus up to n is equal to n into n plus 1 by 2. We all know this thing. Now this is a mathematical equality. It has a left hand side, it has the right hand side. So we can tell this as a mathematical proposition. So what is the mathematical proposition here? Is 1 plus 2 plus 3 up to n is equal to n into n plus 1 by 2. That is a mathematical proposition. And generally we denote it by Pn. That is a mathematical proposition. Correct? Similarly, we can say that for all n belongs to capital N, that is the set of natural number, n square plus n is even number. So it is a mathematical statement, and that also we denote it as a mathematical proposition. Correct. Now let's come to the main topic, principle of mathematical induction. It says that let Pn be any mathematical proposition such that first condition is P1 is true. Number 2 is Pk plus 1 is true when Pk is assumed to be true for some k belongs to capital N, the set of natural numbers, and k is greater than equal to 2. Obviously, why? For k equal to, if k equal to 1, then if k is greater than k is equal to 1, then P1 is coming, which is obviously true. So it has to be greater than equal to 2. If these two conditions hold true, then you can say then Pn is true for all n belongs to capital N, the set of natural numbers. Correct? Let me repeat. Let Pn be any mathematical proposition like this kind of mathematical proposition, Pn 1 plus 2 plus 3 up to n equal to n into n plus 1 by 2, or this thing Pn for all n belongs to capital N square plus n is even number. So these are the kind of this type of mathematical proposition such that number one, P1 is true. P1 has to be true. Okay. Second condition is that if we assume Pk is true for some k belongs to n, the set of natural numbers, okay, then we have to prove that Pk plus 1 is true. That means what? Is that we are assuming Pk is true. Based on that assumption, we need to prove that Pk plus 1 is true. If we can prove that, then you can conclude that Pn is true for all n belongs to capital N, the set of natural numbers. Let's understand by means of an example. So this is the mathematical proposition we need to prove. Correct? So this mathematical proposition is true for, for all n belongs to capital N, the set of natural numbers. Let's see how we can prove it here by means of mathematical induction. What is P1? What is P1? P1 is, or very precisely to say, we can say left hand side of P1 is equal to, only the first term, left hand side is equal to 1, and right hand side of P1 is equal to, we need to put n equal to 1 here, we get 1 into 1 plus 1 divided by 2, that is equal to 1. So what we see, left hand side of P1 is equal to right hand side of P1. That means P1 is true. So left hand side of P1 is equal to right hand side of P1. So this implies, these two together implies P1 is true. Understood? The first condition satisfied here. Second condition is that Pk plus 1 is true when Pk is assumed to be true. That means let us assume that Pk is true for some k belongs to capital N and k is greater than equal to 2. So let Pk is true for some k belongs to capital N and k is greater than equal to 2. So this implies what? This implies 1 plus 2 plus 3 plus dot 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 plus k is equal to k into k plus 1 by 2. Right? Because we are assuming that Pk is true. So according to this assumption, so this will hold true because Pn is the mathematical proposition represented by this equality. So let us keep this as a name of 1. Now, what is left hand side of Pk plus 1? Left hand side of Pk plus 1 will be 1 plus 2 plus 3 plus dot 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 plus k plus 1. Alright? The sum of first k plus 1 natural numbers. Now this is equal to what you can write. You see, this 1 plus 2 plus 3 up to k is nothing but k into k plus 1 by 2, because we have assumed this is true. So that is equal to, we can write k into k plus 1 divided by 2 plus k plus 1. So we are getting that, we are getting by means of the equality 1. Now from these two we can take k plus 1 common. So we can take k plus 1 common, then we are left with k by 2 plus 1. So this is equal to k plus 1 into k plus 2 divided by 2. So that we can write k plus 1 into k plus 1 plus 1, k plus 2 we can write in this way, equal to 2. So that is equal to right hand side of pk plus 1, that is equal to right hand side of p k plus 1, because right hand side of pk plus 1 will be if we replace here in this proposition n by k plus 1, so k plus 1 into k plus 1 plus 1, so k plus 1 plus 1 by 2, so that is right hand side of pk plus 1. So we have proved two conditions, so we can conclude that Pn is true. That means this equality holds true for all n belongs to capital N. So one plus 2 plus 3 plus dot 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 plus n is equal to n into n plus 1 divided by 2 for all n belongs to capital N, the set of natural numbers. So this has been proved. Very quick recap. Okay, we have to prove that 1 plus 2 plus 3 up to n is equal to n into n plus 1 by 2 for all n belongs to the set of natural numbers. So according to the principle of mathematical induction, first we prove that P1 is true. Then we assume that Pk is true. That means this equality holds true. And based on that assumption, we proved by means of these steps that Pk plus 1 is true. That means the left hand side of Pk plus 1 is equal to right hand side of Pk plus 1. Hence, as these two conditions hold true, we can conclude that 1 plus 2 plus 3 up to n is equal to n into n plus 1 by 2 for all n belongs to capital N. Just have a look, quick look, then we will go for the next one. Okay, now let's work on this one, that Pn for all n belongs to capital N square plus n is even number. What is P1? So if we work on this one here, what is P1? P1 is equal to 1 square plus 1, that is equal to 2, which is even number. So that implies what? P1 is true. This implies P1 is true. Correct? Next one, let Pk is true for some k belongs to capital N and k is greater than or equal to 2. So what does it imply? That implies k square plus k is even number. So let us give meaning to this mathematical statement. Let's keep this as number 1. Now what we need to prove? That Pk plus 1 is true. So what is Pk plus 1? Pk plus 1 is k plus 1 whole square plus k plus 1. Now k plus 1 whole square plus k plus 1, that is the Pk plus 1 representation. But whether it is an even number or not, that we need to prove. So that is equal to what? That is equal to k square plus 2k plus 1 plus k plus 1. So that is equal to k square plus k plus 2k plus 2. So 2 into k plus 1. Now k square plus k is an even number. So what you can write? So more specially you can write here, not giving this equation. This implies k square plus k is equal to 2 into m for some m belongs to the set of natural numbers. Right? That is true because it is an even number. So that we can give as a 1. So instead of k square plus k, we can write 2m. Understood, right? So instead of k square plus k, by means of this equality 1, we can write that is equal to 2 into m plus 2 into k plus 1. That is equal to 2 into m plus k plus 1. So it is a multiplier of 2. Whatever the number we got, that is a multiplied by 2. That is a 2 is a divisor of this entire number. So that means it is an even number. So what you can say, that implies pk plus 1 is true. Correct? So we assume pk is true and we are able to prove that pk plus 1 is true. Earlier we proved p1 is true. So we can conclude that pn is true for all n belongs to capital N. So pn, what is pn? N square plus n is even number for all n belongs to capital N. So we are able to prove this one. So this is the boundary. So proof of this first example is here. Proof of the second example is here. What I will suggest, please spend a couple of minutes here and then we go for the next one. Alright. Now, there is a very special case of mathematical induction when you see some mathematical proposition which has been given for some values of n greater than some number. Okay. Suppose, let us understand by means of an example. Suppose this is proof that 2n plus 1 is less than 2 to the power n for all n greater than equal to 3 and n belongs to capital N. What to do? 2n plus 1 is less than 2 power n for all n greater than equal to 3. Then you don't need to give that P1 is true, because P1 doesn't make any sense, because it starts with 3 and more. So P3 you have to prove true. Right? First one. So this is a very special case of principle of mathematical induction, where P1 you don't need to prove. You need to prove the beginning of the value of n for which this proposition is actually mentioned. Here what is the proposition? Proposition is that 2n plus 1 is less than 2 power n for all n greater than equal to 3 and n belongs to the set of natural numbers. So what is our mathematical proposition? Mathematical proposition in this case is 2n plus 1 is less than equal to 2 power n for all n greater than equal to 3 and n belongs to the set of natural numbers. So first we prove that P3. What is P3? P3, let's see what is P3, is 2 into 3 plus 1, that is equal to 7. Okay. And this is less than 8, that is equal to 2 power 3. So what do you see? What is that left hand side of this inequality? That is an inequality. 2n plus 1, that is 2 into 3 plus 1, that is means 7. 7 is less than 8. Obviously. So that means 8 is nothing but 2 to the power 3. So that means this entire expression is less than 2 to the power 3. So what we see? This implies 2 into 3 plus 1 is less than 2 power 3. That implies P3 is true. One thing, though it is not a part of mathematical induction, but it is a part of inequality. See, after 8 I wrote equal. I didn't write less than, because 8 is equal to 2 to the power 3. 7 is less than 8, that's why there is a less than sign. But 8 is equal to 2 to the power 3, that's why there is equal sign. But in general, 7 is less than 2 to the power 3. That means 2 into 3 plus 1 is less than 2 to the power 3. So that is a way to describe mathematical statement. Otherwise it will have, if you write here less than, it will lead to some other meaning. If you write here less than, that means 8 is less than 2 to the power 3. The relation between immediate two statement, which is not true. Correct. So P3 is true. Now we will assume that Pk is true. Let Pk be true for some k belongs to capital N and k is greater than equal to 4, obviously, because for k equal to 3 the proof has already been done. So what does it mean? That means 2 into k plus 1 is less than 2 power k. So let's give this as a name. Now what is left hand side of the inequality pk plus 1? Now what is that? 2 into, now 2 into k plus 1 plus 1. That is the left hand side of k plus 1, be k plus 1, 2 into k plus 1 plus 1. So that is equal to what? That is equal to 2k plus 2 plus 1. That we can write 2k plus 1 plus 2. That is equal to 2k plus 1 is less than, 2k plus 1 is less than 2 power k. That is less than 2 power k plus 2. Right? So that is what you can write, 2 power k plus 2. So that is less than 2 power k plus 1. Correct? So 2 into k plus 1 is less than 2 power k plus 1. Understood? So what we see that pk plus 1 is true. So this implies p k plus 1 is true. So we can write 2n plus 1 is less than 2 to the power n for all n greater than equal to 3 and n belongs to capital N, the set of all natural numbers. So we are able to prove this thing. Just spend a couple of minutes here. Thank you. Okay, so we are done with principle of mathematical induction, but you need to make a practice. A lot of practice you need to do by solving several question papers, several questions from the books, from the different entrance examinations. Okay, so what I'll suggest you that go ahead with the books, like NCERT books, or the questions as appeared in the previous IIT joint entrance examinations. You will get a very fair amount of ideas. I do also have a list of question papers on this particular chapter, so in case you need it, or in case you need any kind of assistance to understand or solution is as there in the book, please do not hesitate me to contact me. Here is my contact email ID. It is kona.classes@gmail.com. Alright, thank you very much. We'll again meet in our next class. Thank you.